And this is talk about, okay, this is from aviation. But basically, I want to talk about this. Keep the big picture and don't get lost in details. Lose your focus on your goal and you lose something important. And that's what I learned from this research. Sometimes it's hard to get the point of the article if you focus too much on each word, some unknown words, or break up with someone for complaining too much about small things. And what I'm going to talk about today is it's really important to keep the big picture, also in CFD algorithm development. I've been working on this economical high-order schemes, something in between the finite volume scheme from the 90s and then the modern high-order methods like DG. I've been saying this repeatedly, but the CFD algorithm development community is trying to make a giant leap from so-called second-order finite volume method from the 1990s to modern high-order methods like DG, Galerkin FR, etc. But still not widely employed in practical CFD codes, not even as an option. And I've been working in between. There are so many things we can do here. Adaptive grids and economical high order, third order, fourth order schemes for unstructured grids or when grids are smooth, high order Navier-Stokes and low dissipation, low dispersion schemes. There are more, entropy stable, etc. And I always feel like we need more people here. And I've been working on node-centered and cell-centered schemes, but this talk will focus on centered algorithm. And I've been developing this special third-order cell-centered method with nodal gradients. This is a unique feature that we store solutions at cell centers, but the gradients are computed and stored at the nodes. And this is the method that has been used in NASA's Vulcan CFD code for hypersonic flow simulations. And as you can see here, this third-order scheme has a very basic baseline second-order method, like finite volume from the 90s, and plus flux correction and the source corrections. And to achieve third-order accuracy, you need a quadratic exactness. You need to compute reconstruct solution from the cell center to the phase center using quadratic interpolation. But here's a unique, very unique quadratic interpolation formula. This is looks like a linear interpolation. And this gradient part is the arithmetic average of the gradient averaged over the phase, this 2, 3, 4. That's this grad WT bar. And grad WJ bar is the cell average of this nodal gradients. And this form is actually exact for quadratic functions if the gradients at nodes are computed by quadratic algorithm. This was a big discovery, and we were able to eliminate second derivatives everywhere. Like flux correction is only requires solution gradients at the nodes. Also source correction, you need a gradient of the source term, which includes time derivative at the nodes. And so this scheme originally proposed for tetrahedral grids, and then recently extended to mixed element grids. And the paper has been published just a couple of like last week in JCP. But in order to take full advantage of this third order implicit scheme, this is only implicit. We need a high order Viscous schemes. We would like to have. So I did it. For unstructured grids, we based on algorithm on the polynomial exactness. So the first thing I did was, okay, what's the Viscous scheme with P2 quadratic exactness? I can use the same interpolation formula, and we need a gradient at phase center, which typically we use average of the nodal gradients plus some jump term, penalty term or damping term. And arithmetic average is exact for quadratic because gradients are linear, and average over the triangle is a linear interpolation. And flux correction, I need this flux gradient, but now the flux contains gradients. So gradient of the viscous flux, you need second derivatives. That's additional cost I have to pay to do P2. But interestingly, if you have if you decide to compute and store second derivatives, you can actually go to P3. And in P3, here's a cubic interpolation formula. And you can derive this correction term to the quadratic interpolation, which requires only the second derivatives of the solution. Usually, cubic interpolation, you need third derivatives. And that's a lot of information, but you can actually eliminate it by storing second derivatives at nodes rather than cell centers. Also, the gradient at the phase center, you need just one correction term. And then this is exact for cubic function and or quadratic gradients. And this is another remarkable formula for flux correction. This correction is needed to integrate flux over a triangular phase, exact for cubic fluxes. But this only requires the gradient of the viscous flux and the viscous flux at each node. So this only requires second derivatives. You don't need third derivatives. So in both schemes, P2 and P3, we need second derivatives of the velocity and the temperature at the nodes. That's all we need. And third derivatives are not needed for P3. And this is a big advantage because third derivative for one variable, there will be 10 quantities. And the 5 variables for naturally Navier-Stokes, you need 50. And computing them and store them is a lot of work. So, and single numerical flux per phase with a high order correction. So now the question, this is a big question. What orders of accuracy do we expect for P2, P3 viscous schemes? Well, in this set, it's very straightforward. We expect P plus first order accuracy for a discretization based on polynomials of degree P. So linear P1, you would get second order accuracy, and P2 quadratic, you get third order, cubic fourth order, but which is not the case for the viscous. From the observations by other researchers, P1 linear second order, and the P2 quadratic, you still have second order accuracy. And the P3, now you have fourth order. So third order accuracy is missing. And so P2 is not enough to achieve third order accuracy, and the P3 gives fourth order. And these have been observed by like Pincock and Katz. They developed a P3 fourth order viscous scheme. And Florian Sethwan at the DLR and his colleagues, they also demonstrated the P2 quadratic scheme is only second order accurate. And I had extensive discussions with these people and still don't understand why. But I tried it with my schemes. And on the left, this is the solution error, discretization error versus mesh spacing. And the P1 is second order, like 1.89. Now P2 is 1.96. This is error versus second order. And P3, now I get fourth order. And why? But this is observed by other researchers. And the P3 is fourth order, it's not third order. And when I look at the gradients, this is X derivative, error index derivative. The second order scheme gives a lower than second order, that's expected. And the fourth order, this is 3.6, but it is essentially third order, that's expected, one order lower. But for P2, looks like I have second order accuracy. And this is, I really don't understand. So P2 gives second order accurate solution and gradients on irregular meshes. But this is also observed by Florian in 2024. So I decided to go down the rabbit hole, try to investigate this in 1D. My biggest question was why is a P2 diffusion scheme of third order accurate? Okay. So this is a finite volume scheme, but the solution is point value. It's like a quick scheme. Muscle, you have cell average, but so we have point value solution at cell centers, and then here's an integral form of the conservation law. The integral is exact, so the accuracy is determined by the accuracy of the interface flux. So advection schemes. In the case of advection, I use this upwind flux. I have the central part and then dissipated part. And solution left and right states at each phase is computed by a high order polynomial. So you have a cell center value and the gradient and the second derivative and third derivatives. And these derivatives are computed by least squares fit over a polynomial degree P. Okay. They're using as many as solution points I need. And this is the truncation error. So the linear P0, that's first order. So the leading error in the truncation error is first order H, and it comes from D. This means this comes from the dissipation. P equals 1, we have second order, and this comes from the central part. And P equals 2, quadratic and third order, and cubic and fourth order, and quadratic and fifth order. So it's very simple. Okay, expect P plus first order accuracy for discretization based on polynomials of degree P. And so here's the summary. Polynomial order of the solution. Zeroth order, you have a second order accuracy from the central part, and first order from the dissipation. And overall, you have first order. When you look at these, the leading truncation error comes from dissipation. In the case of polynomial constant and quadratic and odd order polynomials, the leading error comes from the central part. So 1, 2, 3, 4, but they come from different parts. And here's the irregular mesh results, and everything is as expected. Truncation error, one or the lower. So 0th order, first order, second, third, fourth. And solution error, discretization error is second order, first order, second order, third order, fourth order, fifth order. Everything is clean, and we understand everything. And this is when, now, diffusion. In the diffusion case, the flux is gradient. And here's a general form of the diffusion flux, which has the consistent part, which is the average of the gradient from the left and right. And then here is a stabilization term or damping term. What's unique about this damping term is that we have one over H here. This is needed for dimensional consistency. And here's a pre-parameter alpha. Alpha is 1 for now. And we construct Hiro polynomial for the solution and then differentiate it to get the gradient. So gradient is one of the lower in the polynomial, but these derivatives can be straightforwardly obtained by Viscous fit. Now, so in this case, so we have a solution polynomial, first order, second order, the linear, quadratic, cubic, and quadratic. And the gradients are 0th order and linear, quadratic, and cubic. Central part gives you second, fourth, fourth. And then the damping term, because of this one over H, it gives you second, and fourth, fourth. And they match. This is very different from advection. And overall, we have second order for linear, second order for quadratic, and fourth order for cubic, and fourth order for quadratic. And when I look at this, and this has been verified by numerical results, I get second, fourth, fourth. So now this tells me something. P2 scheme, which is exact for quadratic function, is only second order accurate on regular mesh. Okay. Then there's no way I can expect it to be third order on irregular mesh, right? So in a way, this explains why I don't get third order with P2 quadratic. That's one of the things I learned from this analysis. But at the same time, when I did this analysis on irregular meshes, okay, so the plot on the left is truncation error results on 120 irregularly spaced grids. Okay, so there are so many data points here. I wanted to see the general tendency, and clearly we have 0th order truncation error for P1, first order for P2, second order for P3, and third order for P4. But the solution error is clearly second order, fourth, and fourth, just like regular mesh results. So looks like we have odd order polynomial, P1, P3, we have P plus first order of accuracy for just like advection. But if the order polynomial order is even, P4 and P2 and P4, then we only get P's order of accuracy. So that's why we get this 2, 2, 4, 4. But when I look at this truncation error, this pattern is different. Discretization error 2, 2, 4, 4, but the truncation error 0, 1, 2, 3. And truncation error in this case is a kind of approximation error to the second derivatives. How the discretization is approximating the diffusion operator. So this means if I compute second derivatives, I should get the similar results. So I did. For the second order scheme, I'm not plotting here, but truncation error zeroth order, and actually if I compute second derivative from the second order solution, it will be zeroth order. For P2, truncation error is first order, and actual second derivative is actually for first order. So P3 scheme, truncation error second order, and the second derivative is second order. So they perfectly match. If they match, and we know that the order of accuracy will go down by 1 order if you differentiate. So, and if you go back from the second derivative to first derivative, all right. So the gradient from the second order scheme is first order. If you differentiate this, second derivative should be zeroth order. And then the gradient from the P2 scheme is second order, and differentiated, its second derivative is first order. Everything makes sense. It's 1 order low. And it is, but if I go from gradient to the solution, P1, P3 scheme, 1 order lower grade, that's fine. But again, even order polynomial, you have the same order of accuracy in the gradients and the solution. So, and I still don't understand. If this is solution is third order and fifth order, everything makes sense. It is only this relationship, these two, that I still don't understand. And actually, for diffusion scheme in 1D, you can find special value of alpha to achieve a higher order. And looking at the truncation error, you can find in the P1 case, alpha 7/3, you get fourth order accuracy. And alpha 2/3 for P2 scheme, you get fourth order. And P3 scheme, this special value, 2,413 divided by 990, funny value, but you actually achieve sixth order accuracy. And alpha equals 2/5, sixth order for P4. And yes, but essentially you have basically two distinct schemes here, fourth order and sixth order. And unfortunately, if I try these schemes on irregular mesh, nothing changes. Again, I still don't understand this guy. The gradients and second derivatives and third derivatives, fourth derivatives, everything just lose 1 order, going to higher order derivative. But this step, solution to the gradient, they are the same. So at that point, I've spent a lot of time on this 1D scheme, and I still have lots of questions. So why do we get only P's order accuracy with even order polynomials, while we have P plus first order accuracy with the odd order polynomials? It's a mystery. And how can gradients and solutions achieve the same order of accuracy on irregular mesh with even order polynomials? Another mystery. Is there a way we can achieve third order accuracy with P2 scheme? I think there is, but I don't know. And there are actually, what can we learn from DG diffusion schemes that achieve P plus first order accuracy for any P, like a direct discontinuous garage? There are schemes in DG. This is a well-known problem. Even order of accuracy, or even order of polynomials, you don't get optimal order of accuracy in the solution. And one of the solutions there is to add another jump term of the second derivatives. And I tried it. It didn't do anything for finite-volume. And I still don't understand why adding an additional penalty term will suddenly raise the order of accuracy? I'd like to understand. And maybe we don't care about the slope. I mean, for practical point of view, second order, third order is just the slope. And second order, you just want more accurate solution. And P2 scheme is actually more accurate. So, lower errors and high order derivatives than P1 scheme. So I should be happy. So there are many questions, but is there anything useful developed in this work? And here I realize, okay, now I have to get back to the big picture.
Horace, I think there's someone in the lobby.
Okay. Thank you.
I don't see.
Okay. It flashed up.
Okay. Okay. So recalling the big picture, okay, what am I doing this for? I'm doing this for developing an efficient high order method. And I realized that the P3 viscous scheme that I actually developed was very efficient. And let me explain. Especially for tetrahedral grid, where the cells, number of cells is 6 times the number of nodes. And typically, the conventional finite volume, I think this includes discontinuous galaxy too. With 5 variables, you need to store solution variables, like 5 variables per cell. So 5 times the number of cells is this a long strip of the blue strip. This is an array, like 1D array. And for second order, you need to store gradients. And then you need 3 additional arrays. And for third order, you need a second derivatives too. That's 6. And so in total, you need 10 solution arrays. And fourth order, P3, you need additional 10 arrays. So it's like a 20 times the 20 times the single solution array. But in our economical Nodal-gradient finite volume used in NASA's Vulcan CFD code, we store gradients at nodes. So it requires only 1/6 of the whole solution arrays. Solution is at cell centers, but the gradients are at nodes. And same for third order. And this is very efficient. And when we decide to store second derivatives, now we need to store second derivative, that's 6 quantities per variable, but at nodes, which is 1/6. The same 1/6 of the whole solution array. And we need 6 second derivatives. So in total, we only requires 1 additional solution array. So in terms of memory, it's a tremendously more efficient than a conventional fourth order finite volume, which is very nice and encouraging. So our goal is to develop robust and low dissipation schemes at nearly the same cost of second order scheme for high fidelity, high hypersonic flow simulations on unstructured grids. So the P2, P3 viscous schemes developed here are well aligned with the goal, and details are still important. And I really want to understand. If you know anything, I'd like to learn from you. But we can move forward and get closer to that goal. So here is the conclusion on this for this paper. The P2 scheme is second order on regular grids, and I cannot expect it to be third order on irregular grids. That's one thing I learned, and from the observation of numerical results, we show that P2 viscous scheme is second order accurate, which is a mystery, and the second order accurate for gradients, and P3 viscous scheme is fourth order accurate for solution and third order accurate for gradients. And these schemes are very memory efficient. It only requires additional memory. And future work, of course, if I decide to store second derivatives, then I can do fourth order implicit. And fourth order, now I have fourth order implicit and viscous. The whole thing will be fourth order. And that's what I'm heading to. And further testing for realistic viscous flow performance, of course, it has to be tested. And also extension to mixed element grids. I've already started, and I derived all the formula that I need. I just need to write a code. Okay, so always keep the big picture in mind. Otherwise, I'm dead on the rabbit hole. So that's I'm now coming out, and I think we have something useful. And I hope I'll be able to continue this research and then complete this fourth order Navier-Stokes scheme. Thank you. Plenty of time for questions. Okay.
Yeah, we did study for second order, like one-dimensional problem many years ago, and that was sensitivity. My question actually, so as you started from 1D is a special case, right? Because integration is exact.
Yes, of course.
So at least in 1D, accuracy should be fully related to the flux.
Yes.
So you're saying that somehow when you use your formula for reconstruction of flux, it also shows this behavior, right? So the flux that reconstructed is like for quadratic polynomial, it's only second order.
You mean that? Flux itself?
Flux itself.
I don't know. I didn't.
That should connect because that's the accuracy of flux fully determine accuracy of the solution for this case because integration is exact.
Yes.
So I think somehow in the process that what you're doing degrade accuracy of flux. And I don't know what, but look like that's what happens. At least in 1D case. I'm not making generalization to multidimensional case.
Yeah, but the flux for diffusion is great. And gradient accuracy is as expected.
You can just check it, right? So that you can just compute flux function at the flux location and check it order. And I bet it will be the same order as your solution.
Solution?
Yeah. So it means it will degrade because there is no other in your formulation. There is no other changes that you introduce. So so somehow I think that the problem is that the accuracy of flux is degraded. Not again just conclusion from this observation.
Yeah, flux is great, but you flux teacher is that.
And like for high order scheme, right? So that your value of gradient will change within the cell. So you probably take the value of gradient at the flux location. So there is something actually to check because this is on the boundary, so that the value of the gradient accuracy may degrade.
Yeah, I didn't look at the case of the flux. Mike?
Oh, should I put?
I need to. Oh, now.
Hi, Hiro.
Mike?
So you're discussing mostly
Mike, just a second. You want? Can I do? Okay, it's
is there anything I can do?
Is it sound somewhere?
Mike?
Can you hear me? I guess can other people online hear me?
You can maybe go to Mike and try.
I'll type my question.
To switch it here. I'm afraid of echo.
Yeah, it's strange. Well, let me see. Audio setting.
Okay.
Audio setting is.
Here's the first one for the echo. The first one here, echo coupling down.
This one? Yeah, Mike, could you speak?
I'll try now. Can you hear me now?
Oh, much better.
This is
okay, good. My question's about boundary conditions for the third order or the P3 scheme. So I know you've done some work on higher order boundary conditions. Does it cover how to do boundary conditions for this P3 scheme?
Yes, it's you mean for cloud mesh? I mean curved boundary. I mean for
yeah, I guess for realistic geometry, if you had a BREP CAD model or something for the geometry.
Yes, for tangency condition, I need an accurate normal, and I have a formula, and it has been verified, and it will be presented at SciTech next year.
Okay.
Just like that, yeah.
Okay, thanks.
Yeah, thanks. And hi.
Hey, Hiro. Could you
Hi.
go back to slide 6? I think I wanted to kind of tag along with what Boris was talking about. I was just curious if you'd done any tests of breaking up this into different pieces with the order of accuracy. Meaning, if you, for instance, if you know from the exact solution or the manufactured solution what your flux value should be, then on that third row down where you've got it highlighted in red, the gradient of the viscous flux, if you apply that exact viscous flux there. Have you tested that just to see if you do that, if you recover the design order of accuracy?
To be honest, I don't remember exactly, but this linear interpolation, quadratic exactness, and then this gradient at the face, I think I verified, but maybe I can try again. And yes, for each component, yeah, I have to verify, and so that the whole thing is actually exact for quadratic functions.
And
It's
do you have
important.
Yeah, I'm interested to try this out on my end too, just to as a spot check here, because I'm very interested in why we can't get P3, but it is great that you're able to get the the improvement. I think the fact of the memory savings alone is worthwhile. The other thing I was going to ask was, could you go to your slide? Let's go to slide 20. So one thing that's interesting here that I was just curious if you've thought about is the P1 discretization error and the P3 discretization error have quite a bit of noise in them. And it looks like you ran this with a lot of meshes. Any idea why P1 and P3 are so incredibly noisy compared to P2 and P4?
I don't know. And this is a very interesting feature, yes. Yeah, Boris.
Yeah, there is some randomness effect that is specific to 1D. So there was some paper of Nordstrom and some his students, Eva, I forgot her name. They studied this and they showed that the actual order of convergence has some fractional value in 1D. So it does not hold beyond 1D. But again, 1D is a very special case.
Okay.
And
so
this noise
this in 3D.
actually reflects that the actual order of convergence has some fractional value inside. It's not like h in power integer, it's 8 in power integer. I want to say in half, but I don't remember precisely. I looked at this like 15 years ago, but don't remember.
This fluctuation, I said this is second and fourth order, but it's difficult to say what's the actual.
Yeah, right, the fitting. And the reason it's interesting to me is obviously for heat flux, just because since we're interested at the surface, we see this all the time with mesh adaptation sometimes, where you'll generally move towards the right answer, but you get quite a bit of variance across meshes. So, but if it's not, then that sounds like this is unrelated. If this is a 1D phenomenon, because what I'm talking about would be in 3D. But anyway, very interesting.
And this depends on the size of, like when you have grid irregularity, you have perturbation. So that obviously you need to limit it in order to make sure that perturbed grid are still valid. But you can limit it to various degrees, so that if its perturbation is kind of h square small, not of h small, then you will have more regularity in convergence of these curves.
Yeah. I think for these results, I set the cell center actually to the actual cell center. But if I perturb cell center coordinate, probably this gets much more noisy.
Yeah, exactly.
Yes.
And this was the L1 norm of the error?
Yes. Yes.
Okay.
Yeah.
Great.
Average.
Great. Thanks, Hiro.
Thank you, Kyle. And Doru?
Hi, Hiro. Thank you very much for this very nice presentation. I follow with interest your presentations on economical schemes and high order. This is another one that I'm very impressed. I want to ask you a question. So the return to the big picture. So you want to develop high resolution schemes, economical, for hypersonic flows. So hypersonic flows are not described as necessarily smooth flows. They have discontinuities, large gradients. Is there any concern about how these schemes will essentially perform for this kind of fields? And do you have in mind some special limiting or maybe modifications of the scheme that will in some way take into account the domain of influence, the domain of dependence? The second question is the concern about we have this economical way of constructing the fluxes, but to do this we need high order derivatives, and you go from first derivative, second order accurate to second derivatives now, and that involves more and more neighbors. And although, yes, there are 6 times less nodes than cells in a typical tetrahedral mesh, the number of such nodes that you would need to reconstruct this, second derivatives will grow dramatically, I think, and the cost to compute these gradients will be dramatic. So somewhat, counterbalancing the economy of flux calculation. And so, what are your thoughts in this? Thank you.
Okay, thank you. First, this stencil for the gradient. Yes, it's big, but it's already big for P1 in our case. We compute gradients at nodes and using all the cells around. And in TET, that's already a lot. I guess 50, 60 typical. And for robustness, we actually include more neighbors. The neighbors of neighbors sharing this common node, and that can go up to 200. So even P1, we have up to 200 neighbors to compute the gradient each node. Yes, it's expensive, but that's what we do. And we have enough neighbors to do quadratic and cubic. So I didn't have to increase the number of neighbors because it's already a lot. So, but I know this is a concern. So I've been exploring avenue for implicit gradient method, where I build up globally coupled linear system for gradients at nodes. And then I relax this linear system to get gradients. And in this way, I only need to access just neighbors to do the relaxation. So that's also good for solver stability. So I still keep this as a future option to reduce the cost of computing gradients. And shock capturing, yes, I have to limit this reconstruction. And this is almost like a linear, so I can apply very conventional linear functions. But also I have to apply limiting for flux correction. Make sure that in the limit, I should go back to first order scheme. And this type of finite volume, I also have to limit this source correction time. But this is just like a quick scheme. And for fourth order, I have to limit this flux correction and this quadratic, cubic interpolation, including second derivatives. So I've been trying to develop some algorithm that would work for shock capturing. And but for shock capturing, the benefits of high order is not really too big because it's discontinuous. And typically we go back to first order around shock. But there is a theoretical work that shows that you can actually get higher order, especially for linear shock, linear discontinuity, like contact discontinuity. And so I've been trying to test these P1, P2, P3 up to fourth order in this scheme for shockwave problems involving contact discontinuity to see if we get a large impact of the higher order accuracy. But our target is not really a shock. It has to be robust, but the high resolution, like a vertical structure after the shock. So we'll see how it goes. But the whole point is it has to be as cheap as possible. It must be as close to second order scheme as possible. Otherwise, people would not use it. So did I answer your question, Dory?
Yes. Can I ask one more? Curve
Sure.
shocks.
Yeah.
You have the possibility because we apply fluxes. Riemann. We have Riemann solvers there. There is a possibility of shock attaching to the grid lines and produce this breaking that introduces entropy and vorticity streaks that wash down into the boundary layer, affect like wall heating and skin friction and so on. High order schemes will amplify this effect. Will not help in this particular effect, as it will not help if you have any remnants of the carbuncle issue there. So have you thought about this? Yeah, thank you. This is the last question I have. Thank you.
No, not yet, but that's an important issue, yes. Yes, we'll see what we can do. Thanks, Guru.
Thank you.
Yeah. Thank you.
So Bill, you mentioned moving into mixed elements. So you're talking about fully polyhedral or just the normal reduced set of mixed elements of hexahedral prisms and pyramids?
I think it's arbitrary polyhedral. But I haven't thought about the general polyhedral, but yeah, my focus has been triangular faces and quad faces. So pyramids and prisms and tetrahedral hexa. But I think in principle, the algorithm can be extended to arbitrary.
And will you lose your 1/6 memory savings?
Yeah, you will lose.
Yes, I lose.
Okay.
You will lose.
That's right. So I can't say it's memory efficient anymore for other meshes. So, but yeah. Any other questions? Still have 15 minutes.
What's the state in Vulkan right now? What schemes are already in Vulkan?
In Vulkan, they have a third order indices scheme for mixed elements, tetra and mixed elements, I think. But they don't have this P2, P3 Viscous schemes yet. And a fourth order scheme is not yet. Yeah. My plan is to present this fourth order indices scheme in SciTech January 2026. And summer, I'd like to put them together, Navier-Stokes, fourth order Navier-Stokes schemes, and extend it to mixed elements. So I have a plan, and I hope the budget will follow me. Yes. And I think that Vulkan is trying to have some structure preserving schemes also. That's another important thing to explore for this economical schemes. Yes.
So the question, so a few years ago, you were looking at carrying or solving for the derivatives with a pseudo kind of relaxation, and then we have more equations.
Oh, hyperbolic. Okay.
Right.
Yeah.
This is just kind of brainstorming, but would it be possible to do like a hyperbolic equation set but solving for the derivatives at the nodes, but the primitive variables at the cell centers?
Yeah, that's
as opposed to reconstructing the derivatives.
You will have to carry both cell-centered and node-centered solver together, so that like all volumes will be increased. So
yeah,
I mean, theoretically possible, practically.
That's one of the things actually I've been thinking about. How to apply this hyperbollic Navier-Stokes methodology on this particular discretization. Solutions are cells and gradients are nodes. If I can do this, then I can probably derive the implicit system for gradients, for example. That's as an application. I don't know yet, but Boris, says, like he says, probably I need a node-centered algorithm for the gradients and a cell-centered algorithm for solution.
In some similar way, if you think about finite element, continuous finite element, right? So that the gradient solved actually at cells, well, kind of solution computed at nodes. So, but that's a kind of not a good approximation. You do not actually relax gradients. You just compute them and use them in solution. So that here it will be additional set of equations there. So it's I mean possible, but should be so.
Yeah, that's interesting thing. I still thinking. Yeah. Yes.
I've got a question. Can you go back to where you were talking about the table with the accuracy of the Viscous, the central part and
this one?
Yes. So so here you're showing that they're both the same.
Yes.
So what can I conclude from this, that if you break out the damping term, you have the part that depends on the least squares gradients, and you have the part that depends on what you could call the thin layer gradient or the edge gradient.
Oh.
So I'm taking from this that both of them are second order accurate for the first two rows, and then both of them are fourth order accurate. Is that a valid interpretation of this?
So if you break this UR minus UL into UJ plus 1 minus UJ, and then the gradient
Yes.
terms. UJ plus 1 minus UJ has always the same accuracy, right? Like H. Then the gradient term can cancel this low order. So
Yeah, that's related to flux evaluation accuracy.
yeah. So yeah. Separating them, I don't know what is going. Okay.
Yeah, I guess you have some low order term, and then to get to fourth order, it would be a higher order correction.
Mm-hmm.
Okay.
Yes, yes. And somehow I get second, and fourth on the regular mesh. So
That's the most interesting verification.
yeah. To get third order with P2, I need to have 3 and 3 here.
Yeah.
Yeah, that's what like.
Yeah, but quadratic exactness, simple quadratic exactness doesn't give me that. Yeah, it's a simple Taylor expansion of the scheme in 1D. You see the leading term is second order. Do I have this translation error? Wait a second. Yeah, like this. So this is P1 and this is P2. Oh. So P1, P2, second order, and the leading term proportional to the fourth derivatives. Basically almost the same scheme. Going to quadratic, it doesn't do anything. Just a different coefficient.
Okay. Yeah, it's a relation between going to quadratic and actually reconstructing flux with design order accuracy. That's not the same thing. So that shows right here. That's basically your flux.
Yes. Yes. Yeah, I mean, if you think about the scheme's accuracy on regular mesh, what you need to look at is the truncation error, not the polynomial exactness.
Yeah.
Yeah. So.
But I wonder how it could be exact for polynomial and still below space.
Yeah. And the funny thing is,
So can you go back? So the term is fourth order derivative that multiplies this h squared. So if you exact quadratic, so this term is if you basically zero, right? Because fourth order derivative of quadratic function is zero.
yes, that's true for both P1 and P2.
Right. Right. That right here tells you that it's not enough just to be quadratically.
Yes. So, but you know, in DG, they fix this problem. They somehow achieve the road accuracy with P2 in 1D and also in multi-dimensions, triangular, irregular triangular dimensions. They show the results. And I still don't understand how.
That's interesting because, like, I would expect problems with odd order accuracy for DG. So that, like, for example, that's a known problem. People cannot get first order accurate DG for, I mean, it's P0 for diffusion, right? So that, so.
Yes, P0 is inconsistent. And that's,
But the same thing should affect all odd order polynomials.
yes. So
or even order polynomials.
0 to 4. They are special. And the P0 is inconsistent. And I think that's easier to understand.
But then P2 should be kind of this is the same type of one order degradation.
Yes.
So that from that, if you can understand P0, you should be able to extend this thing into P2.
Yes, because I think I understood why P0 DG scheme is inconsistent. I think I know. Maybe I could extend it.
The same kind of argument should be applicable to even others, even polynomials.
But still, you know, this second order accuracy, the second order solution and the second order gradient on the irregular mesh. This, if I could understand this, maybe we could develop a way to get same order of accuracy for gradients from a numerical solution.
Just not bother, so that okay, you have P1, it gives you second order accuracy, so the next order accuracy is going to be P3. So just not skip over. So because basically you need the same resources, right? So
exactly.
So the same resources, just why if you can have fourth order accuracy, why bother about third?
Yes. So the future work is to develop fourth order Navier-Stokes. Yes, with only a single extra solution array for text. Yes. Okay. No other questions?
It's a very good platform to play with and understand. Easy to produce solution, easy to look at convergence of truncation. So that, it's very useful to develop understanding.
Thank you. So no more questions. It's time for lunch. So thank you very much for coming up. Thank you, everyone.
Thank you.
Thank you.
Really liked this chart right here that you have in the background here.
Oh, this one?
The gut reaction of you need all of these second order derivatives is that, oh no, that's too expensive. But here you're showing.
Oh yeah.
If you want fourth order, you're gonna pay one way or the other. And this is actually cheaper than other ways of paying for it.
Yes. Let's use text.
People stealing from roads.
So speaking from my ignorance, we have, if you have a perfectly structured grid, then you can achieve fourth order using a compact scheme, and then you don't need to carry around second order derivatives.
No. If your grid is structured, there's a better scheme. So it's
And as far as I'm aware, this is where I'm saying it's from my ignorance of the literature. We can't achieve that for general unstructured grids. You can't use a compact scheme where you're doing an implicit solve to achieve fourth order accuracy.
I mean, well, yeah, compact scheme, you mean solving the globally coupled system for derivatives, right? Yes. If structure, you only need the dual derivative and then the neighbor values, right? If you want to do something similar on unstructured grids, it's possible, but you need to build a global system. Your unknowns are not just second derivative, but you have to compute the gradient and then second derivative and third derivative, etc. So, and then you can solve the cis-linear system and get the derivatives at cell centers or node centers. This is what I call implicit gradient method.
Yeah.
It's extension of the compact scheme to unstructured grids. Yes.
And I guess, so then another way to rephrase my question is implicit gradients doesn't get around this problem. That you still need second order gradients to get to fourth order.
Yeah, it's just a different way to get gradients and derivatives. So I don't think it's going to change. But like hyperbolic Navier-Stokes, if you couple the flow equations and the gradient equations fully coupled and strongly coupled, then, and if it is hyperbolic, like hyperbolic Navier-Stokes, then everything becomes clear because it's all advection. So P is the order polynomial, you get P plus first order accuracy for everything, including gradients. So I understand, this way, but if you separate, something different actually happens. So, yeah, use hyperbolic Navier-Stokes, one scheme, test. That's my ultimate goal. That's the future. Oh, and 40. Yeah, that's where we are headed to. Okay. Okay, thank you, everyone. I'm going to end this recording.